Hey guys, welcome to lecture number 13, I think. So in this lecture today, we will talk about limits of functions and continuity. All right, let's get started. Let's dive directly into the subject. Let's not waste any more time. Well, there are a bunch of problems that I want to cover. I hope I will have time for all of them. Oh, what's going on? Okay. Well, sorry about that. So lecture, oh my God, I even forgot to. So lecture 13. Okay, so today is November 24th, right? Okay, that's good. All right, so today we will talk about, just like I said, about limits of functions and continuity. So let's write this. And I will not touch anything about differentiability and continuity. By the way, I'm planning to have a lecture on Thursday. If you guys want to join, it's fine by me. If you don't want to join, it's fine either way. So because I want to stick to the schedule, so that I don't want to lose any lecture. All right. So limits of functions and continuity. First of all, let's start with limits of functions, and I want to cover a few things here. Things that I think you should know, which are very important. And then you will see that we will do a bunch of examples. In fact, I have a couple of problems in mind for this. So the limits of functions, well, let me recall the definition. So, and I'm just gonna, I'm not gonna give you the definition with the neighborhoods, whatever. I'm just gonna give you the definition with epsilon and delta is the same thing. So we say that a function that let's say f has the limit L. And let's just say that this L is a real number, right? At the point x naught. Right? If for every epsilon, if for every epsilon positive, there exists a delta positive such that for all x, so that for any x, let's say, which is this x will be in the domain of the function, but we can take out the point x naught. So for all x in D, with x not being very close to x, so the difference between the two in absolute value is less than delta, we have, so this will imply that f of x minus L is less than epsilon. So that's the definition, right? All right, and there exists a theorem which is very important, and most of you will remember this from Advanced Calc 1. Well, some of you took the Advanced Calc 2 with me, so I didn't have a chance to do this. So the function f defined on a domain D and real value has the limit L right? This L, let's say, is in R bar, so this means that this is can be a real number, and we also include plus and minus infinity here. So this has a limit L at the point x naught. If and only if for any sequence, so if and only if, and I'm gonna, in fact, let me write it like this. So if and only if for any sequence xn of points, let's say, in the domain D, but we exclude that point x naught. We have that f of x n converges to L as then approaches infinity. So that's well, it follows from the definition. And of course you can, what you need to know here is this thing here, imply this. All right, so now what you need to know here is that is this theorem. This is very useful, and you will see that we will use this in a problem. Well, sort of. Well, it will involve more or less continuity. Now, as you can imagine, the usual properties of the limits of functions hold true. I don't need to get into that, as you can imagine. Well, other things that we need to know here is the following. So we can also talk about side limits, right? Okay. So side limits. And what we need to see here is, as you know, I'm going to denote this as f of x minus 0. This is the limit as x approaches x naught from the left, right, of f of x. And so denote f of x naught plus 0. This will be nothing else than just the limit as x approaches x naught from the right of f of x. Right? And of course, you can adapt the definition to this side limit. So this is the left-hand limit, right? F of x naught minus 0, and right-hand limit f of x naught plus 0, right? As you have learned in calculus 1. Now, there is one thing that I wanted to do here is that, so the theorem, it's important here, says that a function f defined on a domain D and real valued, right, has finite, in fact, no, it has side limits right, in an accumulation point this is important. Let's say x naught in D, right? If and only if, guess what? The side limits are equal. Wait, let me, no. Jesus, wait. So, Okay, I want to which has. Here I want to say, okay, which has. So a function which has side limits and an accumulation point x naught has a limit, at x naught, has a limit at x naught, if and only if, guess what, the side limits will be equal. F of x naught minus 0 is the same as f of x naught plus 0. Okay, that's what you need to know. All right, and the main thing, another theorem, and which is very important for you to know, a very important theorem, is that when we have a monotone function, then it has side limits at any accumulation point. So let's state that. In fact, I'll write this with red, or maybe partially. So let D, so this domain will be an interval, be an interval. So a real interval, so in R. And we say that a function f defined on the domain D, real value. So this function okay, a monotone function, so a monotone function f defined on D and real value, right, has always side limits has always side limits at any accumulation point in the domain. So that's what you need to know. You always remember about, keep in mind about this. So you always have accumulation point, and this will be very important when we'll deal with continuity. Well, what else is here that you guys should know? Well, basically this is pretty much it. It's not like, and you know, now you need to, what you need to know is are the famous limits. So very important limits. That's what we need to know at this point. And well, let me point that out. So important limits. So the first one is that, well, sine of the limit as x approaches 0 of sine of x over x is 1. You know this from calculus 1. You can actually prove it using L'Hopital rule. And aside from that, you can say that the limit as how should I say it? As x approaches x naught, let me put it this way, of sine of u of x over u of x, so I'm replacing by a function, this will be 1, provided that the limit as x approaches x naught of u of x is 1. Right? So that's what you need to know. That's the first thing. Let's see another one. In the same fashion goes for the tangent. So the limit for x, small x. Learn this one in physics. Yes, yes, yes. Yeah, you can say that. You can say something like this. Sine of x is for x Small x, yes, you can approximate sine of x with x. But anyway, you will see that all this kind of approximation will follow immediately from the Taylor series expansion. You will see it next week. Anyway, the same story goes for the tangent function. So the lim as x approaches x naught of the tangent of u of x over u of x is 1, provided that the limit as x approaches x naught of u of x is, what did I think I made a mistake here. This is 0 here, not 1. Right. And the same goes here. Okay. What other limits that you need to know? The third one is that, let's see. What else is there? Well, remember this. The limit as x approaches plus minus infinity, if you want, of 1 plus 1 over x, everything to the power x. This is e. Remember that? And the same goes for this one. The limit as x approaches x naught of 1 plus 1 over u of x, everything to the power u of x is e, provided that the lim as x approaches x naught of u of x is 0. Is infinity, sorry about that, yes, infinity. Okay, and now I can, similarly, I can say, let's see, the fourth one, the limit as x approaches 0 of 1 plus x, everything to the power 1 over x is e. And now this will translate into the limit as x approaches x naught of 1 plus u of x, everything to the power 1 over u of x equals e, provided that the limit as x approaches x naught of u of x is 0 this time. All right, hold up, we're not done. There's still some other useful limits. What else is there? Well, there's a generalization of this, so let's write this down. The limit as x approaches 0 of a to the power x minus 1 over x. This is natural log of a for a different than 1. All right. And of course, you can generalize this. You can say that this is the lim as x approaches x naught of a to the power u of x minus 1 over u of x. This will be ln of a, provided that the limit as x approaches x naught of u of x is 0, right? What else is there? Well, in particular, you can take here a to be e. So for a equals e, let's point out this remark here. So in particular, we can take a to be e, and we have that the limit as x approaches 0 of e to the power x minus 1. You have seen this, and we use this, in fact, to deal with some of the, you see, when we deal with the limits of sequences, and we have, I told you we will use limits of functions. And this was one of them. And of course, this can be translated into the limit as x approaches x naught of e to the power u of x minus 1 over u of x. This will be 1. Again, provided that the limit as x approaches x naught of u of x is 0. Okay, so we have this. This thing with the log is just a generalization. Let's see, what else do we have? Okay, so we have this sixth one. If we have with the base of natural log, why not have with natural log as well? So the limit as x approaches 0 of ln of 1 plus x of everything over x. This guy is 1. And the same goes with if we have something like this, ln of 1 plus u of x, everything over u of x. Again, this is 1 provided that the limit as x approaches x naught of u of x is 0. Okay, beautiful. And let's see, do we have anything else? Yes, there is one more, and this is a kind of a Bernoulli approximation. And now, since Jack, you learned this in physics about the sign, probably you've learned about this one as well. But let me. So this thing, it goes like this: is the limit as x approaches 0 of 1 plus x everything to the power alpha minus 1 everything over x. Guess what? This will be what? This will be alpha. Did you learn this about this in physics, in a physics class?
Yeah, I've seen that one.
So you've seen that one? No, in a physics class, not
Yeah, in a physics class.
How did they call it? Did they call it the Bernoulli approximation or?
I don't remember. It was back in high school. I don't think that was anything.
Wow, you did it in high school. Wow, I'm impressed. That's good. So you went to a very good high school. Wow, I did it too in high school, but I did not. I was like, wow, I was so shocked to see that. But, you know, in physics, they said they will approximate. They will say they said something like 1 plus x, everything to the power alpha minus 1 is approximately. So something like this, alpha x, right?
Yeah.
Exactly. Anyway, but this is where it comes from. Okay. And you can generalize this as in the following way: limit as x approaches x naught of 1 plus u of x to the power alpha minus 1, everything over u of x. This will be alpha, provided that the limit as x approaches x naught of u of x is 0. All right, so these are the 7 limits that you need to know. They'll be very useful. In fact, maybe there is a problem. Anyway, I'll do a problem at some point using this. But before we get started with some problems, let me give you, in fact, I have some problems. Let me look here. There was this famous limit. Okay, let me do it. So find the problem 1. I think it's in Putnam and beyond. Find the limit as x approaches x naught of the following. So if, okay, let me put it, if a1, a2, an are positive, then find the limit as x approaches 0 of a1 to the power x plus a2 to the power x plus an to the power x, everything over n. So and everything to the power 1 over x. Okay. I want you to think of this problem a bit until I find that the other problem that I had in mind, I think is some of my old Putnam notes, so maybe I should look it up. Okay. So how would you approach this? So first of all, what kind of indeterminate do we have here? In fact, do you have a guess what the candidate for this limit would be? Hmm? Do you have a candidate in mind?
Maybe something to do with E?
Yes. Yes, exactly. So it will have something to do with E. I agree with that. But maybe do you have like a candidate in mind for this one? Okay, first of all, let's see, what kind of indeterminate do we have? So if you take, so it will be 1 to infinity, right? Correct? So just like Jack said, maybe it will have something to do with E. All right, let's do it. So what should we do? So we would like to apply which limit with E? Let's see, which one is it? Can you tell me based on what in this list? Which one would you choose?
4?
4.
4, exactly. So maybe 4 will be a very good candidate for us to do. But for us to apply 4, what do we need to do? We need to add and subtract 1. So we have, this could be like a Putnam A1 problem, easy. So we have that the limit as x approaches x0, sorry, of, and okay, let me write it again, of a1 to the x plus a2 to the x plus an to the x, everything over n, and everything to the power 1 over x. This would be equal to the limit as x approaches 0 of, and now we should be careful here, so this would be 1 plus a1 to the x plus a2 to the x plus an to the x over n minus 1, and everything to the power 1 over x. Okay, we're not done, so maybe we should write it in a certain way now. So this would be equal to, let's write it further. So this would be the limit as x approaches 0 of 1 plus a1 to the x plus a2 to the x plus an to the x minus n, everything over n. Okay, that's good. Everything to the power 1 over x. So first of all, okay, we established that the indeterminate is 1 to infinity. And now we should do what? We should write this in a certain way. And I'm going to write it in the following way. Don't think I have enough space there, so I'm going to write it like this: is the limit as x approaches at 0 of. So my intention now is to use, we said, which one we said? To use number 4, right? We see it here. Okay. So we like to use number 4. So this would be 1 plus this guy here, a1 to the x plus a2 to the x plus an to the x minus n, everything over n. and everything to the power n over n over what? Over this guy, a1 to the x plus a2 to the x plus an to the x minus n. Okay, let me write it in this way. Ooch. And now I should multiply here by something in such way, so I'll have that 1 over, so what do we have? So we have a1 to the x plus an to the x minus n, everything over n, times x. Agree with me on this one?
Yeah.
All right. So we can write it in this way. As you can see, it's kind of messy. And this will be what? Can you tell me this guy will converge to what? This guy here. This guy in the accolade will converge to what? As x approaches 0, this will converge to?
E.
E, correct. And we know that E will commute with the limit, so this would be nothing else than just E to the limit as x approaches 0 of a1 to the x plus a2 to the power x plus an to the power x minus n, everything over nx. So now at this point, we need to take care of this guy. So we need to take care of this guy here. So what is the limit of this? So now we compute the limit as x approaches 0 of a1 to the x plus a2 to the x plus an to the x minus n, everything over nx. Well, what should we do here? You see, I have 1 over n, let's leave it outside, and this would be the limit as x approaches 0 of, look, we can redistribute that n there, so we can write n as n times 1, right? So it's 1 plus 1 plus 1 n times. And you can write it in the following way, a1 to the power x minus 1 plus n over x, let me write it in this way, plus a2 to the x minus 1 over x plus an to the power x minus 1 over x. And this would be equal to 1 over n. Can you, and here we have something, the limit of the sum is the sum of the limits, right? Let me write it like this so that you can see it. So this will be the lim as x approaches 0 of a1 to the x minus 1 over x plus the lim as x approaches x naught of a2 to the x minus 1 over x plus the limit as x approaches x naught of an to the x minus 1 over x. Well, what can you tell me about each one of them? Now we're using what? Can you tell me about each parentheses? What is the limit of that?
Each one of those is like log AK, right?
Exactly. So this would be 1 over n times ln of a1 plus ln of a2 plus ln of an. And guess what? When you add when you do the algebra here, this would be nothing else than just the square root. Sorry, it's ln of what? Of the product, a1 of the nth root of the product, right? Let me write it in this way. Right? And now, when we go back, keep in mind that the limit is e, so finally, this will give us that finally, it follows that the limit as x approaches 0 of a1 to the power x plus a2 to the power x plus an to the power x over n, everything to the power 1 over x, right? This is nothing else than e to the ln of the end root of the product. Which is nothing else than the end root of a1, a2, an. In fact, this is pretty classical because when you look at the power mean inequality, anyway, this is just the limiting case for the power mean inequality. So it should be expected. So something like this would happen. Is it clear for everybody?
Yep.
Yes.
I think this is in the book Putnam and Beyond. Anyway, this is it's a nice limit, very classical, but all right. Now I want to do another problem. I think it's in some of my old notes. And I look at it. Problem 2. Before I go and dive into continuity, I want to do one more problem, which I think it was some Romanian National Math Olympiad in 1984, which says the following. So let f is a function defined on a 0 infinity real value be a function satisfying that the limit as x approaches infinity of f of x over x to the power k is a number a, right? And k is in n, k greater or equal than 2. Okay, and such that the limit as x approaches infinity of f of x plus 1 minus f of x over x to the power k minus 1. This is number b, and this is again in R bar. Okay, so we have these two, and now we're asked to show that b is k times a. Okay, think about it for a bit. So how would you approach this? Well, if you look at this, like I said, you see, you can reinterpret the definition. Let me go back a bit. You see, I'm going back to this theorem, right? That you can also express this with sequences, the limit of a function in terms of sequences, right? Look at the theorem there. Right, this is the theorem. So that's what we're going to do. So so let's exploit the second condition a bit. So from the second assumption, from the second, I don't know how to call it, assumption, condition, So from the second assumption, we have that the limit as n approaches infinity, so we can consider a sequence, right, of f of n plus 1 minus f of n, everything over n to the power k minus 1. This is b, right? We can say this. And now we define this sequence, let's say u of n to be f of n, right? And b of n to be n to the power k minus 1, where n greater or equal than 1. Now, by the Stochastic lemma, so by the Cezar-Stolz lemma, it follows that the limit as n approaches infinity, well, of un over vn, which in our case, well, is the same as the limit as n approaches infinity of un plus 1 minus vn plus 1. Oh, sorry, minus un. Everything over vn plus 1 minus vn. And this would be equal to, if we write this, so keep in mind that if we look, this guy is A. Look how we can interpret the first condition. Look at the first condition, right? So we can say that the limit as n approaches infinity of f of n over n to the power k, right? So this is A. Right? And this would be nothing else than just what? Than the limit as n approaches infinity. So this would be f of n plus 1 minus f of n, everything over n plus 1 to the power k minus n to the power k. Okay, that's great. And now we would like to write this in a certain way, right? So this will be equal to the limit as n approaches infinity. And now we should be careful here. So we would like to exploit the second condition. So we can write this in the following way. So this would be, let's write it, f of n plus 1 minus f of n over n to the power k minus 1. Okay. And now we're going to multiply. So let's put it this way, times the limit as n approaches infinity of what? Of n to the power k minus 1, everything over n plus 1 to the power k minus n to the power k. We know that this guy, this whole thing here is b. And now we should see what's going on with this guy. So what happens with this guy? That's the main thing we would like to see, right? Okay, so what happens to this? So how should we compute this guy? Let's rewrite it a bit. So we have that. Well, in fact, we should show that this guy is 1 over k, something like this, right? The limit of this. So we have that the limit as n approaches infinity of n to the power k minus 1 over n plus 1, everything to the power k minus n to the power k. So this guy will be the limit as n approaches infinity of, and now let's rewrite this a bit. Maybe we can
Could we use the binomial theorem on that denominator?
On the denominator, so we can,
Because
yeah, I think.
Because the end of the power of k terms would cancel out, and we'd be left with k times n to the power of k minus 1. And then by the limit rules, that's just 1 over k.
Correct. Yes, you're right. Yes, you can do this. And this is, again, it's a very fortunate situation because k is a positive integer, right? But what if k wouldn't be a positive integer? What would you do? Right, you're right, I agree. But let's treat this, because I want to use another limit. Look, I haven't planned to use this 7. You see? Because here I didn't say anything about alpha. Alpha can be any positive number. So I would like to use that, right? So let's see. So let me factor here. So this would be n to the power k minus 1, everything over. So here I should factor n to the power k times, and now let's see. So we'll have n, okay, 1 plus 1 over n to the power k minus 1. And this would be equal to the limit as n approaches infinity of what? Of so this would be 1 over n times 1 plus 1 over n to the power of k minus 1. Okay. And let's rewrite this a bit in the following way. So this is the limit as n approaches infinity of 1 over, and everything happens here on the bottom, so I'll write it in the following way: 1 plus 1 over n to the power of k minus 1, everything to the power 1 over n. Well, what can you tell me about this guy here? This guy will converge to what as n approaches infinity? Can you tell me? This converges to what?
Is that k?
Exactly. So let's go back. Look at this. X is 1 over n. And alpha in our case is what? Is k, right? And that's exactly what we have. So by 7, this is k. So finally, this is 1 over k. And that's it. So finally, A is B times 1 over k. Or B is k times A, and we're done. That's the end of the problem. Beautiful, isn't it? See, we used we use Cezar for limits of sequences, but we also use this this limit function in disguise. Okay, let's see how much time I have. Oh, probably I'll go over time. Now, I think it's a good moment for me to talk about continuity. I want to touch this. It will be a little bit more involved, so probably I'll go over time. So you can log out as any time you want. I'll keep going. So continuity. So probably have seen this before. Anyway, I'm not going to go dwell too much into the definition. Well, the only thing I'm going to say is that well, I would like to talk about something. Well, let's say the definition, or maybe equivalent definitions, let's say. So we say that a function is continuous at a point, right? So we say that, let me say equivalent definitions, the first one. So a function f defined on a domain D, real valued, is continuous, right? If for any sequence, if and only if, for any sequence, let's say xn, with n greater or equal than 1, such that xn converges to this point x naught, right? As n approaches infinity. And of course, xn is in the domain. The sequence f of xn will converge to f of x naught as n approaches infinity. Oops. That's what you need to know, right? Also, we can give epsilon and delta definition. F defined on the real value is continuous if and only if, let's say for every epsilon positive, there exists a delta positive. Let me point out like this. And by the way, this delta will depend on epsilon. Let me delta of epsilon positive. This is important, such that for such that x minus x naught is less than delta epsilon. So it implies, well, of course, for x in D, implies that the absolute value of f of x minus f of x naught is less than epsilon. Okay, so this is epsilon and delta definition. Now, what else? We can say that what is the, well, the usual definition is the limit point, right? So we say that if, so f defined is continuous if and only if the limit, if x naught is an accumulation point, I think accumulation is a double C, or is that right? Anyway, so this is an accumulation point. And the limit as x approaches x naught, yes, with a double C, correct, of f of x is f of x naught, right? Is the value of the function at that point. And what else? A fourth one, because if you want to write this in terms of the side limits, we can say that if, so f how should I say it? if the side limits, let me write it like this. So f is continuous. If and only f of x naught minus 0 and f of x naught plus 0 exist. Both of them exist, and moreover, they're equal, right? And moreover, they're equal. Okay, let me write like this. F of x naught plus f of x naught minus 0 is the same of f of x naught plus 0, and it's the same with the value. Right? It's the same with the limit, and then it's the same with the value of the function at that point. All right. Now, well, you have seen, as you can see here, we have a bunch of definitions of equivalent definition of what it means for a function to be continuous. But now we're wondering, what does it mean for a function f not to be continuous? So we'll call these kind of functions discontinuous. Right, when we have a function that is not continuous at a single point. And the question we like to answer is, what kind of discontinuity points we have? We have, of course, in this case, I'm only talking about discontinuous functions. And we have the following. Oh, well, let me remind you. So how many of them are there? There are 3 types, right? In Romania, there is a funny story. In Romania, we call these first species, second species, and third species. Anyway, or first and second. But in America, it's called, how they're called? Removable, jump, and essential discontinuity, right? So the first one, removable discontinuity. So when do we have a point, when is a point of removable discontinuity? Do you remember? From ACalc 1?
That's just when you have like a single point missing on the curve, right?
Exactly. So the side limits, both of them are equal, right? And they're equal to the limit, but they're not equal to the value. So we have f of x naught minus 0 is the same of f of x naught plus 0. And is unfortunately, they do not agree with the value of f of x naught, right? But we can remove, that's why it's removable. We can remove this x naught, this point, so we can add the limit of this if we want to make a piecewise continuous function. Anyway, what about jump discontinuity? When do we have a jump discontinuity?
Is that when the right and left limits are different?
Yes, both of them exist. So, and they're finite. This is important. And they're finite, but they don't agree, right? But f of x naught minus 0 is not the same as f of x naught plus 0. And the last one is essential discontinuity. So when do we have the essential discontinuity? When both these two guys, they don't exist, or what?
Or they're infinite?
They're infinite. Or they are infinite. Okay. So this is what we need to know. Okay. Now, there is one thing that I would like to address here. Now, this is basically the definition of continuity, but there is one thing very important which is related to continuity. And that thing that it is related to continuity is what we call the intermediate value property. So, oops, intermediate value property. This was found by Darboux in the 1800s, I think in 1821. So not like a long time ago. And it says the following. So let me give you the definition. So let I be an interval right? And let's see, and let this f be defined on this interval, and will be a real value here, be a function. So we say that, so I will abbreviate this by IVT. So we say that f has IVT, so the intermediate value property, right? If for any A and B in any 2 points in the interval I, A, B, right? With A less than B, and for any value lambda between, and this is important, between f of A and f of B. So I cannot say that f of A is less than lambda and less than f of B, because I don't know which one is an f of B, right? There exists a point C of lambda, which depends on of lambda, such that C in AB, sorry. This is in the interval AB, such that f of C lambda is lambda. So this is the intermediate value property. I want you to look at it. In other words, it says that, what does it say? Can you translate this to me?
It takes on all the values between f of A and f of B.
Exactly. That's exactly what it says, right? And as a corollary, we can say the following. And this will be very important in applications, especially in calculus when we do this. It says the following. So if f is defined on this interval I, has intermediate value property. So if this function has IVT, right? And if, let's say we have alpha and beta in the interval, we have 2 points with alpha less than beta, such that f of, let me write it, f of alpha times that f of beta is less than 0, then guess what? Then there exists, let's say, gamma in alpha beta, such that f of gamma is 0. So between any positive and negative value, it will take a value for which is 0, right? That's what it says. Is it clear from the definition? Well, it's pretty much when you take lambda to be 0, right? In the definition, and that's it. Why is this intermediate value property very important? Well, because it will relate with continuity. And basically, we have the following amazing theorem. But before I go into that, let me just say that, so another proposition, which says that if f defined on an interval, let's say, has IVT, then, very important, f of this interval I is an interval as well. Keep that in mind. So this is very, very important. So in other words, we can say that, so what is the relationship? If I ask you, what is the relationship between continuity and the intermediate value property, you will say what? That, which one implies the other?
Continuity implies IVT.
Exactly. So we have that. I'm going to write here big. Continuity will imply the intermediate value property, but not the other way around. Keep that in mind. Any continuous function has the intermediate value property. In fact, let me write it here. So any continuous function has the intermediate value property. The intermediate value property, IVP, not IVT. Where am I? Oh my goodness. Here's IVP. Intermediate value property, not T. Okay. But not the other way around. But there are some conditions. So if we put extra conditions, so there is a gap from the intermediate value property to continuity. But the question is, how far is the intermediate value property from continuity? So that is the question we want to address. So how far is intermediate value property from continuity? So what do you think? So how far do you think the well, the answer is given by the following theorem. So let's call this Theorem 1. And in fact, I'm going to write it like this. Intermediate value property plus injective will give you continuity. So keep that in mind. This word injective here will give you continuity, right? Now, there is another theorem. Well, I'm not going to prove this, Theorem 2, which says that any so you know that any strictly monotone function is injective, right? But not the other way around. So continuity plus injectivity so 1-to-1. When I say injective, I mean 1-to-1. Will give us strictly monotone. Right? Okay. And let's see what else. And from here we can combine this two theorems. So theorem 3. And we can say that if we have a function with intermediate value property plus injectiveness will give us what? Strictly monotone, right? And there's another thing, another theorem, but I'll put it as an exercise, which says that what happens if I have a strictly increasing function and it's surjective? Does this give me continuity? And in fact, I'm going to rephrase this in the following problem. So problem number 3. This was an international mathematical competition in 2006 when I participated. And in fact, I didn't get the full score, stupid me. It was a very easy problem. So the problem says the following. Let me read. So let f defined on R to R be a real function. Prove or disprove, prove or disprove each of the following statements. And it says the following, so let's look. The first one, if, how was it? If f is continuous, so if f is continuous, and the range of f is R, so guess what? This is surjective, right? Then f is monotonic. B, if f is monotonic, I don't know how this is how they state it, and range of f is R, then f is continuous. And C says that if f is monotonic and f is continuous, if f is monotonic and f is continuous, then the range of f is R. Okay, I want you to look at this problem for a bit. I want you to tell me which one do you think is true, which one is false. If you think it's true, prove it. If you think it's false, then provide a counterexample. So let's see. Okay, it's fine. I will just continue, even if you have to go. So let's see. Well, the first one, if we look at it, maybe the first one should, so the first one, A, so we say we claim that this is false. And why should we claim about this? Well, we can consider a bunch of functions, and well, you can see that we can consider a function which is continuous, and the range of f is R. For example, you can take f of x to be x cubed minus x, right? Clearly, the range of f is R. Right? And clearly this is continuous. But now let's see if this is monotonic. Well, it doesn't look this way. Well, if you just, for example, if you look at f of 0 is 0. And if you look at f of 1 is again 0. If you look at f of 1/2 is, what is it? -3/8. So you can say that f of 0 is greater than f of 1/2, right? And f of 1/2 is less than f of 1. Okay, so definitely f is not monotonic. So f is not monotonic. What about B? If we look at B, so in fact this is true, and this is the theorem that I wanted to mention, but I gave it to you as an exercise. So if I have a monotone function and a surjective function, right, onto, so monotone and onto will imply that f is continuous. So this is true. And let's just, without loss of generality, let us assume that f is non-decreasing. Right? So if this is non-decreasing, and we know that since f is monotonic, the one-sided limit exists. So let's just pick an arbitrary number. So pick an arbitrary number, real number, x naught in R. Since f is monotonic, it follows that there exists, so f of x naught, x minus x naught, sorry, and f of x plus x naught exists. Both exist. Okay, that's great. So we know this because it's monotonic. And now we would like to, and since I assume that is non-decreasing, we can say that f of x minus x naught is less or equal than f of x plus x naught. Okay. So if the two limits are equal, then the function is continuous at the point x naught, and we're done, right? Otherwise, so assume that f is not continuous, right? So this implies that f of x minus x naught is strictly less than f of x plus x naught. All right, so there is a gap here. So let's just say this guy is, I don't know, number, whatever. Let's just say this is alpha, and this guy is beta. So we know that alpha is less than beta. And we also know that f of x, so f of x will be less or equal than alpha for all x less than x naught. And we also know that f of x will be greater or equal than beta for all x greater than x naught. Well, now let's look at the range. Now the range of f, which we know that this is R, right? So we have that R, the range of f will be included in this. So negative infinity alpha reunited with a beta infinity. And if you want, we can reunite this with another value, f of x naught. But this cannot complete R. So contradiction. So where did the contradiction come from? So from our assumption that f is not continuous. So therefore, f is continuous. On the entire real line. All right, let's see part C. So part C, well, again, it's false. You can pick any function you want. So I'll leave it to you as an exercise to figure out what kind of function you can pick. Monotonic and continuous, for example, you can pick e to the x, and the range will not be R. So the range is 0 infinity. So f of x is e to the x. Or if you want, or f of x to be arctangent of x, whatever. You can pick whatever you want. So both of these are monotonic and continuous, but the range will be just not the entire real line. Okay, I think I'm going to stop here. Thank you very much.